Welcome to the senior project presentation of Team 8, sponsored by GE Aerospace, the CNC automated part handler, with Ethan Avery, Jasper Bailey, Jacob Kugler, Zachary Moore, and myself, Kayla Lett. GE Aerospace produces a variety of parts for both commercial and military aircraft. This project focuses on a part that goes inside the LEAP 1B engines, which power the Boeing 737 MAX commercial aircraft. This project deals with implementing improvements to the existing manufacturing process of the LEAP 1B shroud. Prior to the development of the CNC automated part handler, an operator was responsible for loading and unloading parts from each station within the machining fixture. Here is Jasper Bailey explaining the current process.
Hello everyone, welcome to GE Aerospace. My name is Jasper Bailey. I am here with Team 8 today. Right now I'm going to give you a closer look at the LEAP 1B shroud process. So right here we have our fixture and it comes fully loaded with parts. There are 4 stations, station 1, 2 deburr stations, and a final 4th station. So when I come here to use this, I need to increment all the parts over to continue the process. So let's start with the last station. I'll pull the part out, and this is a finished part. I'll get the part ready for a wash. Next, I'll increment the part from the deburr station to the final station on the left side. I'll move the part from the right deburr station to the left deburr station. Make sure it's seated properly. And then finally, I'll move the part from the first station to the right deburr station. Next, we have an empty first station here, so we need to fill that up with the raw casting. And to make sure it's located properly, I'll sim check it. And that concludes it. We're good to go.
A safety hazard is presented when operators must handle the mid-process parts due to a buildup of sharp burrs on the shroud. To eliminate the need for the operator to come into contact with these burrs, the CNC automated part handler was developed. The scope of this project was defined as a proof of concept for design. The required deliverables include a functional prototype of the designed tool and written suggestions for future development, as well as an official decision on whether the idea was feasible to pursue further. The design was guided by several key specifications, including a cycle time of 1 minute, a maximum force applied to the shroud of 300 psi, a maximum of 2 operator-to-part contacts for loading and removal, and a limit on the number and complexity of modifications that would be made to the original fixture. A full list of technical specifications was created based on sponsor requirements enforcing limitations imposed by the environment. The limitations created by the environment were found to be the key drivers to the design. The existing environment is contained within a HAAS VF2 series used to perform the machining operations. With 4 stations is used to mount the shroud for each of the 4 machining operations, a grinding operation at station 1, deburring at stations 2 and 3, and a final grinding operation at station 4. The sponsor requested there be no major modifications to the existing fixture that would interfere with the machining operations performed. Based on the provided scope and environment definition, a series of design options were developed. Spindle-mounted, pneumatically controlled parallel gripper option paired with mechanical and pneumatic adaptations to the fixture were selected. This design provided a balance of capability and simplicity while staying within the provided budget. Several design drafts were created, with continuous improvement iterations based on discoveries made during testing. Included concept validation of the radial feature used to open stations 2 and 3, concept validation testing confirming the rotary union design would transfer air to the parallel gripper effectively, measurements to determine the chatter and the spindle orientation hold, and testing to determine the change in orientation of the rotary union after being stored in the tool carousel and brought back to the spindle. The final design for the part handler was created using a combination of custom and stock parts. A custom spindle air mount was designed to intake air from shop lines behind the HAAS and transfer it to the rotary union below. This part will be fixed to the exterior diameter of the HAAS spindle. Press lock pneumatic fittings are used to connect the air lines to the part. Internal channels will redirect the air to female outlets in the bottom of the part, which will mate with male connectors in the rotary union. All seals will be maintained using O-rings. Top of the part handler, a Briney V40E 100-175 tool holder is used to mount the assembly into the HAAS spindle. This version was selected for its easily modified inner diameter and length dimensions. The original part was trimmed down to obtain height required for clearances when the entire assembly is stored in the carousel. A custom rotary union cap was developed to link the remaining assembly with the tool holder. The upper portion would be inserted into the tool holder and held in place with a set screw. The lower portion would run through the rotary union and screw into the pneumatic parallel gripper. The parallel gripper rotation could be controlled by the spindle, while rotary union assembly remained stationary. The core of the part handler design is the rotary union assembly, which is responsible for transferring air from the spindle mount to the pneumatic parallel gripper, while allowing for free 360-degree motion. The assembly is made of 4 parts: the male rotary union, female rotary union, air collar, and male connectors. Male connectors will provide the link between the spindle air mount and the rest of the assembly as discussed earlier. This temporary connection allows the tool and the spindle to be easily removed and replaced, establishing airflow each time it is loaded. The air collar was added to the design to aid in clearances required and tool maintenance. Additional clearance horizontally was required for the tool to fit in the carousel of the HAAS and avoid interfering with tool changes. When thinking about maintenance, the male connectors were found to be the weak point of the design. Should the male connector snap, the air collar allows for easy repair and replacement. The air collar is mounted on top of the female portion of the rotary union. The air channels in the air collar align with openings in the top of the female rotary union, and a seal is created with an O-ring. This channel routes the air to cavities on the interior of the female part. The cavities in the female part will mate with those on the exterior of the male part, creating complete air channels, sealed with X-profile O-rings on either side, while allowing the female and male portions of the rotary union to rotate independently. The air may then pass through an internal channel running through the male part, out nozzles which provide a location for mounting air hoses to connect with the male parallel gripper. Parallel gripper will be held in place via the rotary union cap as discussed earlier. It will also be bolted to the male rotary union so they rotate together, maintaining a stable air connection to operate the gripper. In order to translate the parallel motion of the gripper, custom fingers were designed. The fingers are located using a dowel and mounted to the gripper using bolts. A radial feature was added to the outer edge of each finger to aid in opening levers on the fixture, which will be discussed in more detail later. Each finger has a custom pad. These pads provide a contact surface for holding the shroud. They were designed with both horizontal and vertical profiles to ensure that the part handler could hold the shroud in either orientation. Finally, a compliant mechanism is mounted to one finger. This provides a soft surface to be used in tapping parts after being placed in each station, ensuring they are properly seated without risking damage to the shroud. Some modifications to the fixture are required to accommodate the newly automated part handler. A 3-position 5-way switch was added to Station 1, allowing it to have an open, closed, and neutral position for loading and unloading the part by hand and via the part handler respectively. The piston controlled by the switch is fastened to the station's lever arm via a new custom clevis. New arms were created for each gate with rounded surface to match that of the radius on the gripper finger. These curves allow for the gripper finger to leverage open the gates as it is placing the shroud. ball plungers were also added under the gates so that once they are open a set distance, they will remain open until hydraulics are activated, pulling the gates closed and holding the shroud in place. Small chamfers are added to the outer edges of Station 4 to allow for easier locating when placing the parts. A drop box was designed to hold the completed shroud following being removed from the Station 4 until it can be collected by the operator. This will be mounted on the front side of the trunnion for easy access. The motion of the device is controlled using a G-code subprogram that may be implemented into the existing G-code for the machining processes. The code utilizes the 6 axes of motion available in the HAAS. The table provides the Y and X direction. The trunnion allows for rotational motion about the A and B axes, and the spindle allows for vertical and rotational motion about the Z axes. Initial coordinates for each station location were determined using model simulation. These coordinates were used to create a program which designates travel paths between each location. Optimization was then done in the physical HAAS machine to ensure precise pick and place of the shrouds in the fixture. In addition to the main movement code, the program was divided into several sub-programs, each responsible for a major movement or safety function. The orientation of the spindle, the rotation about the Z-axis, is controlled using a spindle orientation program. This program is built off of the variable number 105, which identifies the current orientation of the spindle, and number 21, which provides the future orientation. An equation was developed to determine the most efficient path for the tool to follow to arrive at its final destination. An integrated safety program was also developed to monitor the forces required to move in any given direction. If one of these forces is greater than the set limit, indicating a potential crash, the machine will emergency stop and move to a safe position so an operator may solve the issue. 2 variations of this program were developed, one for linear motion and one for arced motions. For an additional safety check, a pressure switch was installed to monitor the air pressure received by the parallel gripper. Should the air line disconnect or pressure fall outside the determined bounds, a flag will be raised and the program will stop so the issue may be addressed. The parallel gripper being used is normally closed, so if air pressure is to be lost, no shrouds will be dropped. For a complete cycle, the tool is first loaded into the spindle. The part will then be removed from Station 4. And taken to a drop box for the operator to collect later. The shroud in Station 3 will then be removed. And loaded into the newly opened Station 4. The compliant mechanism is then used to tap the shroud, ensuring it's seated properly. A part is then removed from station 2. And loaded into the newly opened station 3. Finally, an air cylinder is activated to open the lever on station 1, and the part is removed. And loaded into station 2. The full movement cycle is now complete. To begin a new cycle, the operator may open the HAAS doors, remove the finished shroud from the drop box, load a new raw casting into station 1, close the doors, and hit cycle start. This process may be repeated indefinitely to create the shrouds required. Following the development and testing of the part handler, it has been proven to be a feasible design option, but will require further development and integration to be used effectively in production. The key specifications of operator-to-part contacts, minimal modifications, budget, and force generation were met. The cycle time and repeatability are currently the main concerns for the design. Some future improvements are recommended to help alleviate these concerns and improve upon the design's efficiency. Adding a light box to confirm the seating of the part in each station will ensure repeatable and proper loading of the shroud into each station. Using a PID controller would allow for easy adjustment to account for belt slack and variations in the machines, and more streamlined orientation of the spindle. Currently, the air is controlled via a manual switch for proof of concept stage. This should be wired directly through the HAAS and controlled using the G-code so that the process is fully automated. Finally, the current design for the male connectors causes the O-rings to be sheared, leading to unnecessary wear. A spring adjustable design would be allowing a single O-ring under crushing force to create the desired seal. While the design, particularly with this improvement, is a viable solution, it is recommended that a robo-cell similar to that used in other areas of manufacturing be implemented for this application. This was limited by the project's budget in this case.